In chemistry and physics, a nucleon is one of the particles that makes up the atomic nucleus. Each atomic nucleus consists of one or more nucleons, and each atom in turn consists of a cluster of nucleons surrounded by one or more electrons. There are two known kinds of nucleon, the neutron and the proton. The mass number of a given atomic isotope is identical to its number of nucleons. Thus the term nucleon number may be used in place of the more common terms mass number or atomic mass number. Until the 1960s, nucleons were thought to be elementary particles, each of which would not then have been made up of smaller parts. Now they are known to be composite particles, made of three quarks bound together by the so-called strong interaction. The interaction between two or more nucleons is called internucleon interactions, or nuclear force, which is also ultimately caused by the strong interaction. Before the discovery of quarks, the term strong interaction referred to just internucleon interactions. Nucleons sit at the boundary where particle physics and nuclear physics overlap. Particle physics, particularly quantum chromodynamics, provides the fundamental equations that explain the properties of quarks and of the strong interaction. These equations explain quantitatively how quarks can bind together into protons and neutrons and all the other hadrons. However, when multiple nucleons are assembled into an atomic nucleus, nuclide, these fundamental equations become too difficult to solve directly. See lattice QCD. Instead, nuclides are studied within nuclear physics, which studies nucleons and their interactions by approximations and models, such as the nuclear shell model. These models can successfully explain nuclide properties, for example, whether or not a certain nuclide undergoes radioactive decay. The proton and neutron are both baryons and both fermions. They are quite similar. One carries a non-zero net charge, and the other carries a zero net charge. The proton's mass is only 0.1% less than the neutron's. Thus, they can be viewed as two states of the same nucleon. They together form the isospin doublet, I equals 1, 2. In isospin space, neutrons can be rotationally transformed into protons, and vice versa. These nucleons are acted upon equally by the strong interaction. This implies that strong interaction is invariant when doing rotation transformation in isospin space. According to the Nether theorem, isospin is conserved with respect to the strong interaction. 129-130. Protons and neutrons are most important, and best known for constituting atomic nuclei, but they can also be found on their own, not part of a larger nucleus. A proton on its own is the nucleus of the hydrogen 1 atom, 1H. A neutron on its own is unstable, see below, but they can be found in nuclear reactions, see neutron radiation, and are used in scientific analysis, see neutron scattering. Both the proton and neutron are made of three quarks. The proton is made of 2 up quarks and 1 down quark, while the neutron is 1 up quark and 2 down quarks. The quarks are held together by the strong force. It is also said that the quarks are held together by gluons, but this is just a different way to say the same thing. Gluons mediate the strong force. An up quark has electric charge plus 2,3e, and a down quark has charge 1,3e, so the total electric charge of the proton and neutron are plus e and 0, respectively. The word neutron comes from the fact that it is electrically neutral. The mass of the proton and neutron is quite similar. The proton is 1.6726 × 10^27 kilograms, or 938.27 MeV/C2, while the neutron is 1.6749 × 10^27 kilograms, or 939.57 MeV/C2. The neutron is roughly 0.1% heavier. The similarity in mass can be explained roughly by the slight difference in mass of up quark and down quark composing the nucleons. However, detailed explanation remains an unsolved problem in particle physics. 135-136. The spin of both protons and neutrons is 1, 2. This means they are fermions, not bosons, and therefore, like electrons, they are subject to the Pauli exclusion principle. This is a very important fact in nuclear physics, Protons and neutrons in an atomic nucleus cannot all be in the same quantum state, but instead they spread out into nuclear shells analogous to electron shells in chemistry. Another reason that the spin of the proton and neutron is important is because it is the source of nuclear spin in larger nuclei. Nuclear spin is best known for its crucial role in the NMR/MRI technique for chemistry and biochemistry analysis. The magnetic moment of a proton, denoted P, is 2.79 nuclear magnetons, and while the magnetic moment of a neutron is N equals 1.91 north, these parameters are also important in NMR/MRI. Stability. A neutron by itself is an unstable particle. It undergoes decay, a type of radioactive decay, by turning into a proton, electron, and electron antineutrino, with a half-life around 10 minutes. See the neutron article for further discussion of neutron decay. A proton by itself is thought to be stable, or at least its lifetime is too long to measure. This is an important issue in particle physics. See proton decay. Inside a nucleus, on the other hand, both protons and neutrons can be stable or unstable, depending on the nuclide. Inside some nuclides, a neutron can turn into a proton, plus other particles, as described above. Inside other nuclides the reverse can happen, where a proton turns into a neutron, plus other particles, through plus decay or electron capture. And inside still other nuclides, both protons and neutrons are stable, and do not change form. Antinucleons. Both of the nucleons have corresponding antiparticles, the antiproton and the antineutron. These antimatter particles have the same mass and opposite charge as the proton and neutron respectively, and they interact in the same way. This is generally believed to be exactly true, due to CPT symmetry. If there is a difference, it is too small to measure in all experiments to date. In particular, antinucleons can bind into an antinucleus. So far, scientists have created anti-deuterium and anti-helium-3 nuclei. Tables of detailed properties. Nucleons. Nucleons, I equals 1 2. S equals C equals B equals 0. Particle name symbol quark content res mass, MEV/C2, res mass, U, I3JPQ, E. Magnetic moment mean lifetime, S, commonly decays to proton PDG1P/P, +/N, plus UUD 938.270.0000231.0000727646770.000000000 10 plus 1212 plus 12.7928473560.000000023 stable be unobserved neutron PDG2N/N0/N0 UDD 939.565346091597.0000000000004 3 minus 1212 plus 01.91304273.000000045 8.8570.008 102 CP plus E plus E antiproton P/P/NUUD 938.2720130.0000727646770.0000000000010 minus 1212 plus 12.7930.006 stable be unobserved antineutron in/N0/N0 UDD 900 39.4850.051.0008664915970.00000000043 plus 1212 plus 0 8.8570.008 102 CP plus E plus plus E. Circumflex. The masses of the proton and neutron are known with far greater precision in atomic mass units, U, than in MeV/C2, due to the relatively poorly known value of the elementary charge. The conversion factor used is 1U equals 931.4940280.0000023 MeV/C2. The masses of their antiparticles are assumed to be identical, and no experiments have refuted this to date. Current experiments show any % difference between the masses of the proton and antiproton must be less than 210 pdg1, and the difference between the neutron and antineutron masses is on the order of 9.6-10.5 MeV/C2 pdg2. Proton-antiproton CPT invariance test formula RPG result pdg1 mass 210 charge to mass ratio 0.99999999910. 0.0000000009 charge to mass ratio 99, 10 11 charge to 10 9 electron charge 1 10 21 magnetic moment 0.12.1 10 3 circumflex B at least 1035 years. C proton decay. Circumflex C4 free neutrons. In most common nuclei, neutrons are stable. Nucleon resonances. Nucleon resonances are excited states of nucleon particles, often corresponding to one of the quarks having a flipped spin state, or with different orbital angular momentum when the particle decays. Only resonances with a 3 or 4 star rating at the particle data group, PDG, are included in the stable. Due to their extraordinarily short lifetimes, many properties of these particles are still under investigation. The symbol format is given as an M, L2I2J, where M is the particle's approximate mass, L is the orbital angular momentum of the nucleon meson pair produced when it decays, and I and J are the particle's isospin and total angular momentum respectively. Since nucleons are defined as having 1-2 isospin, the first number will always be 1, and the second number will always be odd. When discussing nucleon resonances, sometimes the N is omitted, and the order is reversed, giving L2I2J, M. For example, a proton can be symbolized as N, 939, S11 or S11, 939. The P11, 939, nucleon represents the excited state of a normal proton or neutron, for example, within the nucleus of an atom. Such particles are usually stable within the nucleus, i.e. lithium-6. Quark model classification. In the quark model with SU2 flavor, the two nucleons are part of the ground state doublet. The proton has quark content of UUD, and the neutron, UDD. In SU3 flavor, they are part of the ground state octet, 8, of spin 1-2 baryons, known as the eightfold way. The other members of this octet are the hyperon strange isotriplet plus 0, and the strange isodoublet 0. One can extend this multiplet in SU4 flavor with the inclusion of the charm quark to the ground state 20 plt, or to SU6 flavor with the inclusion of the top and bottom quarks to the ground state 56 plt. The article on isospin provides an explicit expression for the nucleon wave functions in terms of the quark flavor eigenstates. Models. This article may be confusing or unclear to readers. Please help us clarify the article. Suggestions may be found on the talk page, August 2007. Although it is known that the nucleon is made from 3 quarks, as of 2006, it is not known how to solve the equations of motion for quantum chromodynamics. Thus, the study of the low-energy properties of the nucleon are performed by means of models. The only first principles approach available is to attempt to solve the equations of QCD numerically, using lattice QCD. This requires complicated algorithms and very powerful supercomputers. However, several analytic models also exist. The SCARML models the nucleon as a topological soliton in a nonlinear SU2 bion field. The topological stability of the SCARML is interpreted as the conservation of baryon number, that is, the non-decay of the nucleon. The local topological winding number density is identified with the local baryon number density of the nucleon. With the pion isospin vector field oriented in the shape of a hedgehog space, the model is readily solvable, and is thus sometimes called the hedgehog model. The hedgehog model is able to predict low-energy parameters, such as the nucleon mass, radius, and axial coupling constant, to approximately 30% of experimental values. The MIT bag model confines three non-interacting quarks to a spherical cavity, with a boundary condition that the quark vector current vanish on the boundary. The non-interacting treatment of the quarks justified by appealing to the idea of asymptotic freedom, whereas the hard boundary condition is justified by quark confinement. Mathematically, the model vaguely resembles that of a radar cavity, with solutions to the Dirac equation standing in for solutions to the Maxwell equations, and the vanishing vector current boundary condition standing for the conducting metal walls of the radar cavity. If the radius of the bag is set to the radius of the nucleon, the bag model predicts a nucleon mass that is within 30% of the actual mass. Although the basic bag model does not provide a pion-mediated interaction, it describes excellently the nucleon-nucleon forces through the 6-quark bag S-channel mechanism using the P matrix. The Curl bag model merges the MIT bag model and the Scarum-Eon model. In this model, a hole is punched out of the middle of the Scarum-Eon and replaced with a bag model. The boundary condition is provided by the requirement of continuity of the axial vector current across the bag boundary. Very curiously, the missing part of the topological winding number, the baryon number of the hole punched into the Scarum-Eon, is exactly made up by the non-zero vacuum expectation value, or spect relay symmetry, of the quark fields inside the bag. As of 2006, this remarkable trade-off between topology and the spectrum of an operator does not have any grounding or explanation in the mathematical theory of Hilbert spaces and their relationship to geometry. Several other properties of the Curl bag are notable. It provides a better fit to the low-energy nucleon properties, to within 5–10%, and these are almost completely independent of the Curl bag radius, as long as the radius is less than the nucleon radius. This independence of radius is referred to as the Cheshire Cat Principle, after the fading to a smile of Lewis Carroll's Cheshire Cat. It is expected that a first-principle solution of the equations of QCD will demonstrate a similar duality of quark-baryon descriptions.